Good morning to everyone. For some of us, it's good afternoon, and for a few ambitious people, it's good evening. I think there's a few people from the different time zones. So today we're going to talk about the closure of mine tailings and sediment ponds. And just to start off, I want to be clear that we're not confusing the closure of ponds, or in fact the capping of ponds, with the closure of mines. I mean, mine closure is a discipline in its own right. It's quite broad and it's generally done over many years, and there's a number of materials, some references on the right there, but there's a number of materials that can explain what mine closure is. Today we're talking about the closure of mine tailings and ponds, and that very well may be part of a broader mine closure. And to just set the scene, in mining, water management is very important, and every mine site will have their own issues. So generally, in mining, you've got either too much water or not enough. You might have it in the wrong location, or you may want to reuse it, but it's too dirty or contaminated. There's a number of challenges, and you have got your own terminology as well about what type of ponds you have. So you can see I've listed out there a range of names that mining companies or mine sites will call their storage facilities, and I'm sure there's many more. And some photos on the right will show the scale. So they can range from being reasonably small, say 30, 50,000 square metres, all the way up to being 300,000-400,000 square metres in size. So the key point here is every mine site is pretty unique in its water management issues. But generally, there's a number of ponds on a site. So if we look at a water or liquid containment pond on a mine site, geosynthetics can be used in 3 different applications. The first is when you're actually building the pond. You may use geosynthetics if you're lining it, so things like geomembranes or GCLs, as well as other materials. And then when the pond is in use, you may want to be dewatering it, removing the sediment or sludge from the water. So you can use geotube dewatering, and occasionally, if you're more towards the end of life, you might be looking to dewater it using PVDs perhaps. And at the end of the useful life of the pond, you may wish to come back and cap it, and that's where we'll be talking today. And there's 2 solutions that are used in capping of a pond. You can either cap it with a lining solution, such as again membrane or GCL, and that's pretty much done to make sure the rainwater coming in does not get into the sludge underneath, or alternatively you let the contaminants below come up. Or you may be looking to reinforce the top of the pond, which will be the focus of what we talk about today. And essentially what you're doing there is putting soil on top of a very, very soft sludge. And why would we want to close it or put a soil layer on top? Again, every site will be different, but there will be a number of reasons that could apply. You might operate in a country where you just have to do it. It's part of your mining license or regulations. You might be part of a global company and have your own internal frameworks to work within. It might have a safety or environmental aspect, such as you don't want, after you leave site, you don't want people wandering in or livestock wandering in and falling in the pond, or the pond itself overtopping and emptying into the river. So there's a number of reasons that you would actually close the pond down. So this is the classic situation where you've got your pond wall and your saturated sludge inside. One way of putting the cap on is actually, rather than just using the building on top of the saturated sludge is to dewater it, and that'll be the discussion around the next talk. But not all sludge actually dewaters that well. It might be that we've put it in too quick, or you're in a high rainfall area, or perhaps that the nature of the sludge is such that it just doesn't consolidate. So today we're going to step through the solution where we're putting a pond capping, or for example, in our case, a metre of fill on top, and we're putting a reinforcement solution on top of that sludge so that we can build on top of it. So the problem we're trying to solve is moving from this application or this solution to this, where you can see that we've put a soil layer on top of the saturated sludge and allowed the vegetation to come back, and the landform returns to some form of original vegetative environment. And the red line there signifies the geosynthetic reinforcement layer. So we want to get to this solution without this happening, where you think you're building on top of a stiff crust, or on top of drier tailings that actually, or drier sludge than is actually there. And of course, what happens is you break through the crust, and then you find yourself in trouble with machinery or people starting to sink down. So that's what we don't want to happen. And here's an example of what we'll be talking about today. So this is a mine site in the Northern Territory in Australia. On the left is what it looked like many years ago, in the turn of the century, at 2000, and you can see the pond was in action. And today, it's back to a natural landform. So they could have just filled that up with sediment and then built on top, and they could have dewatered it out, or they could have capped it. But at the end, what their intent was to get a layer of soil on top, and so they can vegetate it, revegetate it. So that's the situation we're talking about. So if we've got a pond with very soft sludge, we need to be able to get construction access out there to place the reinforcement solution, as well as place the soil layer. So we need that. That's why the reinforcement layer is there. It needs to separate the sludge from below with the material on top. It needs to allow water flow, and it needs to have good tensile strength. And the number, or the strength of the material, we'll select during the design phase. And the other point is we've got to make sure we've got a continuous sheet of reinforcement. So whether we supply the reinforcement solution in panels or rolls, during the construction phase, we don't want the adjacent panels or rolls to come apart. So we'll talk a little bit about seam strength and overlaps as well. And Tenkate have been offering solutions for pond closures and pond cappings for decades, and the proven reinforcement solution from our perspective is a high strength woven geotextile sewn into large panels, and the sewing can be either done in the factory or on site. But we'll be talking about a high strength woven solution today. So the best way to step through is maybe take quite a simple example, and then we can move through the 6 steps. So for today, let's just assume that we've got a sediment pond on a mine. It's next to a river. We don't want it to overtop or fail and go into the river and impact the downstream communities. It's a relatively small pond, so 30,000 square metres. It's, the sediment depth 4 metres, and then the freeboard, that is from the height of the the water level to the top of the dam bank of 1 metre. So the decision has been made that we need to close the pond. We don't operate under any regulations that would mean that we have to line the cap, so we can use a 1 metre thick cover layer. You can call it a store and release cover, but essentially what that means is a thick soil layer that, as the rainfall comes, it's stored within that layer and then is released later, so that the rainfall is not going through that 1 metre thick cover layer and into the sludge beneath. So one of the advantages of being able to use a woven geotextile is generally we can take the mine overburden waste and use as the cover material. And there might be a few selection characteristics around that, but what it does do is enable you to use existing materials. So what we'll do now is just step through our approach and see how we can solve the problem. So in simplistic terms, there's 6 steps. The first 3 all relate to what's going on site. So what's the characteristics of the sludge, what cover materials or equipment do we have, and what are the pond dimensions. The 4th stage, obviously the design phase, can be done at the desk, and stages 5 and 6 is where they start to move beyond design and actually out into the field and dealing with the contractor and all the practical considerations around buildability, safety and so forth. And on the right hand side you can see that this is what the characteristics will influence. So for example, the sludge characteristics will determine the strength grade, the construction method and so forth. So there are reasons for determining the inputs. So if we start with looking at the sludge, you can look at the pond and you can try and determine that if your crust is stiff or soft, but that's the best way to do it is, or the only way really to do it, is to actually determine the undrained shear strength. It's one thing to look at it, it's another thing to know what's going on beneath the surface, as well as how consistent the undrained shear strength is across the pond as well. So if the actual geotech report comes back and says you've got some reasonably good strength for that crust as well as beneath it, then the simplest and cheapest method is just to build on top of it. Option 2 is where it's kind of middle of the range, and you may have solutions where you can stiffen it a little bit. So you may dewater the sludge, or alternatively, if you're confident, you may want to have the geotech people look at placing thin layers of dry tailings and building it up. But you'd want to know for sure what's going on beneath the surface. But there are many instances where that sludge is actually either soft on the surface or soft beneath the surface, and you need to reinforce it. And that may be in instances where you've actually filled that pond quickly and it hasn't allowed the material below to evaporate out. It might be in high rainfall areas, or it might just be that the poor consolidation properties of the sludge itself. But option 3 is where we're looking today. It's a proven solution. The installation is a little bit more complicated than the other solutions, and it is also a little bit more expensive than the other solutions as well. But the key point is when you're building on soft sludge, sometimes it may be the only solution. And the point about the geotech report is that if you break through the crust, you may find yourself in a lot of trouble. And I showed the photos before of the mining vehicles. And here's a video where this chap is out on a pond, standing on the crust and thinking it's pretty strong. But if you watch him, I'll just try and play that again. can see as he punches through the crust how soft it is underneath, and with hindsight perhaps he should have been wearing a safety harness or similar, but you can see the point there that whilst that crust looks stiff, in actual fact underneath it's pretty weak. So you'd want to know the undrained shear strength of the sludge. There's a couple of ways of doing it, but the in situ vein shear test is the best way. There's also other ways, like on the right hand side there, you can see them taking some test results across what looks like a pretty weak surface. A high quality geotech report at the start will give benefits later on. You know, I think it's all well and good to have one result, but you'd want to know across the width and down the depth at a number of locations exactly what we're dealing with, because that'll yield what we're building on. So today we'll just assume we've got a very low undrained shear strength, therefore we need to use a reinforcement layer. The other influence will be where exactly is the water in relation to the sludge. So on the left hand side you can see there the water level sitting pretty much at the saturated tailings level or just below, whereas on the right hand side there are going to be mining ponds where there might be 3 metres of water depth or 5 metres of water depth above the tailings or the sludge. They're very, very different construction modes, and they bring different challenges. So for the purpose of today, in keeping it simple, we'll assume the most common solution or application, which is on the left hand side where the sludge is actually sitting above the water level. And you can see that'll enable us to access the surface far more easily than on the right hand side. Another detail we should determine with the sludge is the pH, and this is more just a check for short-term durability. So with a mining pond closure, you might be dealing with environmental regulations that'll start talking in hundreds or thousands of years, but the geosynthetic reinforcement is not required for that long. So the geosynthetic reinforcement is there for the initial years in terms of durability, and is there mainly to take up the load during the construction phase, because over the longer term, you know, the actual cover layer will help put downward pressure and push the water out of the sludge below, and it'll stiffen it up a little bit. But the key point is that the geosynthetic reinforcement has got to last at, you know, perhaps a year, and it's got to be, given that geosynthetics are made from polymers, it's got to be compatible with the pH. Now, the chemistry of pH will vary. This is a good paper. It generally outlines the different liquors or outputs from the mining processes, and it then correlates that to the common polymers that geosynthetics are made from. So for the point of today, we'll assume a pH, pick a value of say 3 or 4, which is generally well accepted for the impact on common geosynthetic polymers. Having said that, we are looking at jobs with pHs as low as 1.2 and 2. So it's just a matter of having test results available. But for the point of today, we'll assume the pH is pretty plain vanilla. Step 2, just want to check determine the loads, and the loads are coming from 2 areas, one of which is the cover material that we're putting on top. So that'll be what run of mine waste have we got lying around the site that we're going to use in that 1 metre thick layer. And also, if we've got some details around it, we'll be able to understand any installation damage, strength reduction factors and so forth that we can use. And I'll show you some photos of why. I mean, high strength woven geotextiles are quite accepting of big angular rock, but notwithstanding that, we've got to take into account what the cover material is, and as well as the impact it has during the construction phase. And then the live loads. So in this case, that's the equipment that's being placed on top. And again, for mining sites, it's generally you're generally starting off trying to use the equipment that's on site and not trying to bring other equipment in. But that'll all be factored into the design phase. So for the point of today, let's just assume that we have a 300 mil drainage layer, and then we put a 1 metre thick capping on top, and we're making that capping layer from the available overburden or mine waste, and we know what construction machinery we've got as well. So this will give us the inputs into the design phase. Next is we've got to understand the pond dimensions and how they relate to the geotextile panel sizes or a little bit in the buildability phase. So we'll assume a pond of 100 metres by 300. It's not very big. Some dams, as I said before, can be 200, 300,000 square metres or bigger. We can supply high strength woven geotextile in reinforcement in panels. From the factory, the benefit of this is the seam strengths achieved in factory made panels are higher than on site, and seam strengths may play an important role later on, which we'll talk about during the construction phase. So for this pond, we are able to make rolls of 125 metres length, so longer than the 100 metre length, and panels of 25 metres wide. So that's 5 rolls stitched together. So in this case here, we would need 9 panels. Now the 9th panel may not be 25 metres wide, but you can see the logic that take the pond dimensions and start to figure out how many panels you need. So now we step into design. So we've got our knowledge around the sludge. We've got our knowledge around the loads, as in the machinery loads and the construction and the cover material loads, and we understand the dimensions of the pond and the panel layout. So we're going to design using tension membrane principles, and which essentially means, as you can see here, that as you put load on, you'll get some deformation, and you're placing that reinforcement layer in tension, that's the design method will reflect this. And you can also see there'll be, as I said, deformation. The sludge will move, and we'll show you some of the impacts that need to be considered later. So in terms of design, I'm not going to step through it. What I will point out is there's 3 very good papers. They all build on each other. So from 87, 99, 2008, and the 2008 paper actually gives a worked example as well. And these papers provide a good basis for design. And they can also support your own design methods with your own software, or proprietary software. So you want to be looking for the local and global failure, and in this case here, you've got it's a fly ash pond. You've got a 1 metre thick layer using a woven. In this case, it's an RS 580i. You've got your dozer on top, and essentially you're checking that you've got the right factors of safety. So the key point is that there are established methods for this, and they're laid out in those papers, and you can support that with your own checks through software. Now, if the sludge is very weak, as the cover material is placed, you're going to get stresses along the seams. So the seam strength needs to be understood. And I mentioned before that factory seam strengths can get a higher result than in situ seaming. This is where you need to understand or apply judgment that, for example, in situ seaming, you can do trials, and you might be getting 30, 35%, maybe 40% of the strength across the seam, depending on capability of the stitcher. In the factory, depending on the capability of the teams, you can get north of 50%. So the seam strengths play a role in the design as well as overlaps. And I'll show you a little bit about overlaps later, but in essence, that's to stop the panels moving whilst there's settlement. And the berm dimensions and spacings will be confirmed through the design process. So I'll show you some photos of what the berms look like, but essentially all that's taken care of through the design. Step 5 is we're now moving into the practical side of it. You can see on the right hand side, that's a panel that's for the Hong Kong Airport project, recently been completed. You can see that when you're talking about panels that can weigh over, over 1 tonne, over 1,300 kilos or more, you need to have a detailed understanding of how you're going to handle this at each stage. So how you're going to handle it in the factory, how you're going to handle it in and out of containers. Open top containers are generally used on road transport as well as on site. And this is more around safety, but it's also making sure the panels don't get damaged along the way. And the last step is actually where all the construction tips and tricks come into it. So we'll talk about installation a little bit, and then I'll show some photos and a couple of case studies. But spending a bit of time thinking it through about how to construct it and getting it right in the planning process will make life a lot easier when you actually come to build it, because it's a bit hard when all the panels are on site and you're trying to pull it across and it's not quite working. So this is a bit of a summary slide. You can see that if they're the panels laid this way, you've got seams, you're putting some anchorage load around on the panels, and then you're working perpendicular by pushing out finger berms. And that's where I said before, the dimensions of the finger berms and the spacings can all be worked out in the design phase. So let's just go through quickly, step by step. This is plan view. The panels will be delivered to site. They'll need to be unfolded, but essentially what you've got here is the pond walls and the saturated sludge. You're then rolling the panels out. So you can see here that you have overlap with the edge. As you've rolled it out, you'll probably want to ballast the edge to resist uplift. You're then taking the next panel out. You want to overlap the panels. In this case, I've mentioned 1 metre, but that's just a number. The key thing is, how are you going to pull these panels out? Remembering these are 125 metre long panels, so you need a lot of planning around what equipment you've got, how you're going to pull it so it doesn't damage the product, and you've also got to make sure it's being laid accurately. Having got it in and having anchored the ends, remember that we had a 300mm sand layer, so we then start to place the sand layer over the geotextile, working perpendicular to the principal strength direction, which is from left to right. And after we place the sand layer, we then start to introduce the tensioning finger buns. Now, what they do is start to tension the geotextile. So this is the principal reinforcement direction, and by working out this way, you slowly put it in tension, and that way you're not overstressing it. So you need to move carefully, and you can see there the lightweight dozer, but obviously we've done that design to knowing what equipment we've got that we're working with. And then having put the buns in place, we can then fill in between. So in essence, you're filling in the palm between the fingers, and then you progressively keep going forward with your sand and your finger buns, and then filling. All the time working perpendicular. So if we step through now a number of photos just to see some concepts in action. In this case here, it's a single panel, big rolls that are you can see the seams going this direction and being pulled across. See the the webbing that's pulling it across. Is because it's going on the water. You've got floats on that leading edge. And that's one way of getting it across. Here's an example of the soil layer being laid on top. You see a little bit of a mud wave there, but working perpendicular to the principal reinforcement direction. But you may have instances where you don't have a soil layer. You may just want to go straight into the tensioning buns. In this case, it looks quite small, and you can see the seams running up from top to bottom and just coming across from either side. And that's quite a valid way of approaching it as well. And the point of this photo is to show that sometimes the mud wave can be quite significant, and if you're putting load on and the sludge beneath is moving that much, you've got to be able to ensure that your material stays together. So those seam strengths are important and need to be considered so that you're not having gaps open up within the reinforcement layer. And an aerial shot of a project in China where all the panels are laid out. You can see some ballasting probably for uplift. That's all buried in around the edges for anchoring trenches, and then progressively moving out with the material so that you're progressively tensioning putting the reinforcement into action. And in this case, they're working from the side, but there's also some equipment moving slowly out, pushing the materials around. So I've got 3 case studies to show examples of what we've just talked about in action. This is one in the US where you think you've got a good crust and you open up beneath and it's just sludge. So in this instance here, you can see the equipment coming in. You've got rolls of woven geotextile. In this case, it looks like it's only 2 rolls wide. There's one seam down the middle getting pulled out. There's the seam there. They're pulling it in a certain way such that the material doesn't rip or tear, and just pulling it out progressively, placing it down. Again, you can see the seam, and then you get that separation, you get strength, and you also get some, the water or the liquid coming through as well. So you get that release of pore water pressure. And the point I made before about the use of cover materials and how wovens, geotextiles can be quite accepting of a broad range of materials. If you look here, that's quite big rock being used. Quite, it's going to have a bit of impact on the geotextile as it's placed, and you're not going to get that with many other geosynthetic solutions. So this is a great photo showing, in this case, no drainage layer. They just took the existing run-of-mine waste and pushed it back out and created a soil cover on top of a woven geotextile as reinforcement over a weak sludge below. Another example is in Spain, a tailings pond that was being closed, a reasonably large one at 350,000 square metres. You can see there that the material was very soft, and they were going to build a 1 metre thick working platform on top. So this is a bit of an aerial shot showing the reinforcement layer being installed. This is the cross section, so a 400 kilonewton reinforcement layer, 400 kilonewtons in both directions, with a 1 metre stone working platform. Again, you can see the type of stone used, so not as big as shown in the US example, but still reasonably large. And the difference here was, once they had the working platform in, they then built up another 1.5 metres or more, but they had to line it, and they had to put in a geomembrane liner to stop the water coming down and getting into the sludge below, as well as contaminants coming up. So slightly different, but in this case, looking at the reinforcement layer, it was holding up nearly 2 metres of soil on top, and obviously did the job on very soft tailings with construction vehicles working on the top. And the last case study is a mine pit closure in Australia, and you can, at the start I said we're talking about pond closures, not mine closures. In this case, the mine was being closed, but you can see there from 96 to 2008 they were filling up the this pond, and sometimes mine closure is done progressively over decades, so they're actually doing it whilst they're operating. So in this case here, they were planning ahead for closure whilst they were placing their waste. They came back 2012, put some PVDs in, came back a few years later and then put in the high strength geotextile layer. So in this case it was a biaxial 150 kilonewton Marafi PT or polyester woven, again a reasonably big area. So the cross section, there's the tailings, there's the reinforcement layer, so the PVDs were coming 40 metres down. So the reinforcement layer was placed in a 2.5 metre rock cap, and that took care of all the rain that would come in, get stored and then evaporate. Now, obviously with PVDs, as you put the waste rock on top, it pushes down and then the water comes out and you stiffen up the sludge below. So the stitching was done on site rather than in factory, but the photos will show why. It's quite a big area. So that was it, 2000, obviously, all liquid. This is what it looks like, 15 years later. The first stage was putting the PVDs in, a little bit tricky. They had a barge, big mast, punching the PVDs down. So you can see that in this case, the water level was above the sludge. The high strength woven that was delivered to site was sewn on site to provide the seams, and then it was progressively laid out. So you can see that whilst it had now provided a bit of a crust, compared to the water before, the machinery and the rock layer would have gone punched through that crust. So they're putting the reinforcement layer down and slowly working their way across. You can see here the reinforcement layer just building across. A little bit of a closer photo. They had multiple layers of geosynthetics. The black layer here is just a cheap slick film woven on top of the PT 150 kilonewton biaxial reinforcement layer. And this is probably the photo that shows it best, where they've actually got the reinforcement layer being installed and putting the finger berms in and then filling in between. So slowly working their way in from around the edge. And that's what it looks like today. So that's the end of my talk. Hopefully you learned a little bit around reinforcement of a pond closure capping, and I'll hand back to you, Hardy, and thank everyone for their attention.